This should be a quick one. We're just going to review very quickly how redox reactions work. Before we jump into all the electrochemistry stuff, we need to just kind of go back over some stuff that we've already hit on earlier in the year, and it's going to be, we've talked about it a couple times in the last couple of AP packets, but we need to make sure that we remember how to do oxidation numbers and how to identify the oxidizing, what's being oxidized, what's being reduced, oxidizing agent, reducing agent, all that stuff. Okay. All right, so Leo goes Gur is going to be your friend again in this unit. Lose electrons means oxidation, gain electrons means reduction. Okay. Now, problem is when you look at a reaction, it's not going to be immediately obvious a lot of the times which one is gaining electrons and which one is losing electrons. So we need to find the oxidation number of the element. And through the course of going through a few of these, we will review over some of those oxidation number rules that you had to remember. I guess I'm not going to go over all of them point by point on this video. I'm going to assume that we can look back and remember those, but throughout the course of going through these reactions, hopefully most of them will be covered. So on our example here, one thing to remember about oxidation numbers is that the elements that are in their most naturally occurring state, we're going to assume they have oxidation numbers of 0. Okay, so for example, this zinc right here has an oxidation number of 0 because that's the way that zinc usually occurs as an element when found in nature. It's just by itself. Now, another rule is that typically the charge on a cation or anion is going to be equal to its oxidation number. Okay, now those two things are not exactly alike, and we're going to talk about that in just a minute. And we talked about that the first time we covered this as well. They're not exactly alike. Oxidation number does not exactly mean charge, and I'll show you why in just a minute. But when you have something that has a charge, like this H plus here, its oxidation number is also going to be 1 plus. Its charge is 1 plus, its oxidation number is 1 plus. Okay? And there are 2 hydrogens there, so overall that's a 2 plus charge, but each of the hydrogens has an oxidation number of 1 plus. Alright? Now if we come over to the other side, the zinc is going to have an oxidation number of 2 plus over here because it has a 2 plus charge. And then H2, that's its most naturally occurring state for hydrogen, so that's going to have an oxidation number now of 0. Okay? And so, remember, if you have an oxidation, there's also going to be a reduction. Electrons can't just leave something and go nowhere. So if one thing is losing electrons, then the other thing is going to be gaining electrons. Right? So the zinc here, you can see it goes from a 0 to a 2 plus charge. Okay? Which means it is becoming more positive. Okay? Now electrons have a negative charge, so if something's becoming more positive, that must mean that it's losing electrons. Okay, so this is the oxidation. The zinc is getting oxidized. Okay, now the H plus here is going from a 1 plus oxidation state from here to a 0 oxidation state. Okay, and so this is actually going down in charge. It's going from 1 plus to a 0. It's becoming more negative, which must mean that it's gaining electrons. And also we can assume that it's going to do the opposite of what the other one does. Gain electrons is going to be reduction, so hydrogen is the one here that is getting reduced. Okay? Now I don't know if I was meaning to go over all of that or if I was just wanting to talk about oxidation number here. But you can use the oxidation number to figure out which one is getting oxidized, which one's getting reduced. Okay, another example here that might be slightly less obvious because there are no charges in this one. We can figure this one out as well if we look at the oxidation numbers on these things. Now I'm going to put the oxidation number above it here because I don't have a lot of room below it. The H2, again, is going to have an oxidation number 0. So is the O2 because both of those are in their most naturally occurring state. Now we come to a couple of the rules that it would be good to remember. If you have a hydrogen connected to a non-metal, then its charge is typically going to be 1 plus. Okay? If the hydrogen is connected to a metal, then it's going to have excuse me, you're gonna have a 1 minus. I said charge, I meant oxidation number. I apologize. So let me back up and say that again. If the hydrogen is connected to a non-metal, like oxygen, its oxidation number is going to be 1 plus. Okay. If it's connected to a metal, like NaH, sodium hydride, or something like that, then its oxidation number would be 1 minus. Okay. Now again, that's not its charge, because this is a covalent compound, okay? But that's its oxidation number. So the hydrogen here, because it's connected to a non-metal, is going to have a +1 oxidation number. Now, another rule is that oxygen is almost always a 2 minus or a -2 oxidation number, okay? And the exception there is when it's in a peroxide, like H2O2, then it will have a -1 oxidation number, okay? Or if it's combined with something that's more electronegative than itself, which is basically just fluorine. Okay, so if it's combined with fluorine, then that's another exception. Then the fluorine is always going to take the minus charge, and then you give the minus oxidation number, and then you give oxygen whatever oxidation number you need to in order for it to balance out. Now again, something we need to remember here is that when you add the oxidation numbers of these two things, they should equals 0. Okay, and there are 2 hydrogens here, each of them with a +1 oxidation number, so that's overall a 2 plus oxidation number of 2 plus, and then a 2 minus from the oxygen. You add those up, that's going to equal 0. Okay, so that's a way to check yourself and make sure you're doing your oxidation numbers correctly. Alright, so now we can look at this. The hydrogen here is going from a 0 to a +1. It's becoming more positive, which means it must have lost electrons. So that's Leo. That's oxidation. And the oxygen here is going from a 0 to a -2, so it must be gaining electrons. That's Ger. Oxygen is getting reduced. Okay? Now again, there's not a complete transfer of electrons taking place. This is not an ionic compound. H2O is covalent. Okay, so again, we're not talking about charges here. We're talking about oxidation numbers or oxidation states. Okay, so you got to understand they're not quite the same, especially when we're talking about covalent compounds. They're not the same. Okay, oxidizing agent is the substance that causes another substance to be oxidized. In other words, it's the substance that gets reduced. Okay, and then a reducing agent is what causes something else to be reduced. So it's the substance that gets oxidized. Okay, so here's a good example of this. Now I could go back and show you just real quick on this one. Because the H2 is getting oxidized, it is the reducing agent. It's the thing that's causing the oxygen to get reduced. Okay, and because the oxygen is getting reduced, it is the oxidizing agent. It's the thing that's causing the hydrogen to get oxidized. Okay, so that you just kind of have to remember that they're backwards from one another. Okay, so here's the example. The nickel-cadmium battery uses the following redox reaction to generate electricity. We want to identify the substances that are oxidized and reduced and indicate which are oxidizing agents and which are reducing agents. Okay, so in order to do this, we're going to have to figure out some oxidation numbers here, and this is kind of a long one, but we should be able to figure this out. So cadmium, solid. Okay, cadmium's a metal, and metals typically in their solid state, that's their most naturally occurring state, so that's going to have an oxidation number of 0. Okay. Now the nickel oxide here, NiO2, we just kind of have to follow our rules. Now nickel is a transition metal, so it's difficult to know exactly its charge here. This NiO2 is an ionic compound. Okay, you got a metal and a non-metal. So in this case, we do have charges associated with these things. But the nickel is going to have various charges that it can have since it's a transition metal. So we want to start with the oxygen here. The oxygen has a 2 minus charge, and there are 2 of them. So I'll write a 2 minus up here. And then, hang on just one second, sorry. Okay, so sorry about that, very quickly finishing this up here. So we had said the cadmium had a 0 oxidation state. The oxygen has a 2 minus. There are 2 of them. So I'll put the oxidation number of each oxygen down there, and then I'll put the overall at the top. So if this is a 4 minus overall coming from the oxygen, the nickel needs to be a 4 plus. And then we just did H2O. The H2O, you're going to have a 2 minus for the oxygen, and you're going to have a 1 plus for each hydrogen, which adds up to a total of 2 plus overall. Then on the other side of this thing, now what I like to do with OH is think about the fact that that is OH minus. Okay, treat it like a polyatomic ion, and that's going to help me. Now, this turns out not to be that difficult because if the oxygen is a 2 minus here and the hydrogen is a 1 plus, then you add those together and it adds up to the charge on the ion. So this is going to be a 2 minus and a 1 plus. Okay. Now, overall, there are 2 hydroxides there. So the overall charge coming from, again, this is an ionic compound. Okay. So these are charges that we're talking about, and the charge is going to be equal to the oxidation number. So the OH minus, there are 2 of those. That's overall a 2 minus charge coming from the hydroxide. So the cadmium here must be a 2 plus charge to balance that out. So it's going to have a 2 plus oxidation number. Okay, same thing on the OH over here. And it's going to be a 2 minus and a 1 plus again because it's the same polyatomic ion. The nickel is also going to be a 2 plus. Okay, so at first glance you might have thought maybe the hydrogen or the oxygen gets reduced or oxidized here, but they don't. The hydrogen and the oxygen both stay the same oxidation number on both sides of the equation. So the things that are getting oxidized and reduced are the cadmium and the nickel. All right. So the cadmium is changing from a 0 to a 2 plus, which means it's getting more positive. So this is the one that's losing electrons, and that's Leo. So this is getting oxidized. Okay, and then the nickel is going from a 4 plus to a 2 plus. So it is actually becoming more negative. It's gaining electrons. So it's the one that's being reduced. Okay. And then again, you just have to remember that they're opposite of one another. Since the cadmium is the one that's getting oxidized, then it is the reducing agent. And since the nickel is the one that's getting reduced, it is the oxidizing agent. Okay? Alright. I feel like I put one more example on the back of your notes. Let me check and see if that's the case, or maybe that's the example we just went over. There's one more. Okay, the oxidation state of oxygen and hydrogen peroxide. And we actually just talked about that. I don't know why I didn't put that on the notes, but that's on the back of your note sheet. So H2O2, okay. And again, the thing that you need to remember here that will help you on this one is that hydrogen, when it's connected to non-metals, is going to have an oxidation number of 1 plus, okay? So if this hydrogen has a 1 plus oxidation state, and there are 2 of them, then overall that's a 2 plus, which means that the oxygen, to balance that out, because there's no charge on this molecule, it's going to have to be a 2 minus oxidation state, okay? If it's a 2 minus oxidation state, and there are 2 of them, then each of the oxygens would have a 1 minus oxidation state. Okay, so the oxidation state of oxygen in hydrogen peroxide is going to be a 1 minus. Okay, I think that's it for that. Hopefully that is a good refresher on how to do these oxidation numbers and how to figure out what's being oxidized and what's being reduced. And we'll jump right into some more electrochem stuff starting tomorrow.